The breeze is pretty strong, and I hear some rustling sound in the previous podcast. Sorry about that, but seems to be quite audible, so you have to just imagine the wind as you're listening to the sound and not get upset. So the thermohaline circulation brings us into paleoclimate as well, as we said, but first we may want to just briefly orient ourselves towards orbital forcing. This is a little animation from NASA which shows how the ellipticity of the Earth's orbit around the Sun changes on a 100,000 year time scale. Obviously here the Earth is coming closer and going farther from the Sun at 100,000 year time scale, which means the amount of energy being released is going to change as well. I'm not able to paint so cutely. Oops. Okay, never mind. But the change in energy because of this small change in eccentricity is not really that great. It turns out that there is another mode of variability in the orbital forcing called the precessional forcing, which happens here on the 23,000 year time scale, and it turns out that the 100,000 year time scale and 23,000 year time scale of precession and ellipticity can combine to produce a dominant beat in many of the records of past climate variabilities. So here we are looking at today what the configuration is in terms of where the equinoxes, autumnal and spring equinoxes happen, and where the summer and winter solstices happen, and how that changes. So Milutin Milankovitch did the mathematical calculations of how the orbits change, so you can very precisely say these things now. So 5,750 years from now you will have a change where the solstice will happen on September 22nd and equinoxes will and March 20th, whereas equinoxes will happen on December 21 and June 21. So this is called the apsidal precession, where the orbit itself keeps spinning because of the gravitational pull from the other planets in the solar system. So obviously if we live that long, we have to adjust the calendar to keep our equinoxes and summers and winters in the same place. So 11,500 years from now you will again flip, and then 16,725 years from now one more flip, and then you will come back to the current configuration in 23,000 years. Okay, so there is also an axial precession, which I think I can only play if I go and come back. Oops, sorry, I was trying to play this again, but there we are. So the ellipticity changes, the precession of the axis changes this way, so that where the north pole is pointing will change as well. And on a 41,000 year time scale we have a change in the this doesn't work unless I go back and come back. Okay, so where the obliquity also changes with respect to the orbital plane between 22.5 to 24.5 degrees on a 41,000 year cycle. So these together produce the ice ages on a very long time scale. How do we know that? We basically use what are called geochemical tracers or proxies, and delta O18 is one of them. We are used to thinking of oxygen as having 8 protons and 8 neutrons with the mass number of 16, but as you can imagine, you can always increase the number of neutrons keeping the element and its properties the same. So you have what is called O18, where you have 8 protons and 8 electrons, but you have 10 neutrons, so you get O18. And the fractionation of O16 and O18, knowing the standard components or standard amounts in regular oxygen, we can look at old samples from ice cores, from ocean sediments and other origins, and relate it to how the temperature would have changed in the past. How do we do that? Basically, we define what is called delta O18, where we look at the O18 to O16 ratio in the sample of ice core or ocean sediment, lake sediment, or whatever other source, and we compare it to a standard that is maintained very delicately somewhere, and that O18 O16 ratio -1 tells us how depleted or surplus the O18 is in the sample that we are looking at, typically from the past. It's multiplied by 1,000, so it's written as parts per thousand. So in a percentage you have a slash and 1 0 on each side. For parts per thousand, you have 1 0 at the top and 2 zeros at the bottom. So instead of parts per 100, we think of parts per thousand, because these are small numbers. So how does it work? Essentially, if you think of water that is evaporating, H2O, so you have some amount of H2O16 and H2O18. Evaporation is basically a process of ripping hydrogen bonds, lifting water molecule out of the ocean or land, lakes or soil moisture or whatever. Let's stick to the ocean. So when evaporation happens, it is energetically more efficient to pick up H2O16 because it is lighter. So the evaporated water in the atmosphere tends to be less of O18 than O16 because it has picked up more O16. So water slightly depleted in O18 evaporates from the warm subtropical waters. But this O18 depleted water, as it moves towards the poles and it rains along the way, the heavier water molecule H2O18 falls preferentially because it's heavier than H2O16. So the water gets continuously depleted of O18 as it gets to falling as snow at polar regions, let's say in Antarctica. And snow in the interior of Antarctica then has 5% less O18 than the ocean water, because as it evaporated and was depleted in O18, it kept on getting depleted along the way and is heavily enriched in O16 and 5% less O18 than ocean water. So if we go in the past and look at how depleted the water is, then we can begin to estimate how enriched the O18 is in the ocean. We can then estimate how much glaciation may have happened, because if the ocean water has more O18, then it means that less O18 has been buried in glaciers, which means there may have been more glaciation during that time. So you have to nail down the timing using other methods of geochemical tracers like carbon molecules C13 and C12 or C14, which is a dating carbon isotope which is unstable, or you have other isotopes which allow you to date. So you need to date to see when the sample was collected, and then you need to estimate what temperature could have been present at the time. So typically you don't get absolute measure of temperature. What you get is a relative measure of temperature compared to the baseline, which means you get anomalies of the past climate with respect to some baseline in the present climate. Okay, similar to global warming. When we look at global warming, we typically tend to compare to a base period like 1961 to 1990, or the post-industrial period, and so on. So this is how paleoproxies work. That's a very quick introduction. There are many details that we didn't consider here. So this is Chris Karnauskis' book, the schematic from the book Schematic illustration of the mechanisms leading to oxygen isotopic fractionation, which means O16 and O18 amounts are changed. Evaporation and precipitation lower the delta O18 content of the water in the atmosphere, which subsequently fall on land, as I just explained, and raise the delta O18 content of the seawater if it decreases. If you move water into the atmosphere by depleting O18, then that O18 is left in the ocean, which is subsequently incorporated in foraminifera shells buried in layers of seafloor sediment. Cold climate conditions with large global ice volume are thus recorded as high delta O18 in benthic records and low delta O18 in ice core records. So foraminifera are these calcifying shell animals. They die, the shells fall to the bottom, and they are preserved, and the amount of delta O18 in them tells you when they formed, what the temperature would have been. So evaporation lowers delta O18 by preferential addition of O16 because of energetic constraints. So high delta O18 water remains in the ocean and is incorporated in foraminifera shells fossilized in seafloor sediments. So isotopic fractionation continues during precipitation, which means more of the O18 water falls, so it lowers the delta O18 further by preferred removal of O18. So low O18 water precipitates onto continents, forming glaciers, which is now enriched in O16. Okay, so let's leave this here and come back and look at a couple of long time scale paleoclimate records. So since these paleo proxies don't measure temperature directly, they're called proxies for temperature. So they are indicators of temperature change in the past based on these chemical signatures. I closed the window. I'm still getting a lot of wind from the other window from the other room, so hopefully the sound is not too bad. So I will check and see. Okay.